Okay, good morning, good day everyone. For today's video, ang ating topic is elasticity. So ito yung elasticity ng mga object or body na a-applyan natin ng mga forces. So, introduction nito. When an external force is applied on a body which is not free to move, the shape and size of the body will change. The force applied is called the deforming forces or deforming force. When the deforming forces are removed, the body tends to regain its original shape and size due to the force developed within the body. The force developed within the body, which is equal and then opposite doon sa deforming forces, is called the restoring forces. The bodies which completely regain their original size and shape after the removal of deforming force are called the elastic bodies. The bodies naman which change the shape, wait lang ha, gagawin lang natin. So, huwag yung kalimutan, yung mga bodies na after ma-applyan ng mga deforming forces and then nakabalik sa kanyang original shape and size are called elastic bodies. Yung bodies naman that change the shape and size on the application of force and will not regain or do not regain the original condition on the removal of the deforming forces are said to be plastic bodies. So hindi na siya makabalik sa kanyang original shape and size. And then the bodies naman which do not change their shape and size on the application of the deforming forces are called to be rigid bodies. Okay. The property by virtue of which a body tends to regain its original shape and size after the removal of the deforming forces is known as the elasticity. Okay. So next tayo. So here we have the elastic modulus. The elastic modulus in general relates what is done to a solid object. A force is applied to how that object responds or kung paano siya ma-deform to some extent. Ang stress naman is the quantity that is proportional to the force causing a deformation. The external force acting on an object per unit cross-sectional area. Next is yung strain. Strain is a measure of the degree of deformation. And then here we have the elastic modulus formula. So we have elastic modulus is equal to the stress over the strain. Or elastic modulus is the external force acting on an object per cross-sectional area over yung degree of deformation natin. So next we have, let's tackle about the stress. So yung formula ng stress natin is force over area. And then ang definition ng ating stress, when an external force is acting on an elastic body, it causes deformation or change in shape or size or both. At the same time, due to elastic property, a force is developed within the material, which is equal and opposite to the applied force to bring the body to its original shape and size. This is called the restoring force. So ito nabalikan na natin kanina. So huwag niyo kalimutan ang definition ng ating restoring force. So once na-applyan siya ng deforming force, yung ating object, and then after i-remove natin yung forces na yun, yung applied forces natin, is bumalik din siya sa kanyang original shape. Yung force na nag-contribute or nagpabalik dun sa body to its original shape and size is yung kanyang internal restoring force, or nasa object mismo itong nasa object mismo itong restoring force na ito, or within the body of that object. Next, the stress is defined as the restoring force acting on a unit area. Since the applied force and the restoring force are equal in magnitude, the stress is measured as the applied force acting per unit area. When the applied force tends to compress the body, the stress is called compressive or compressive stress. When it tends to increase its length in the direction of the force, kumbaga mainat siya, it is tensile. And when it acts parallel to the surface of the body, the stress is tangential stress. Okay, next. Next is ang Hooke's law. So what is Hooke's law? So define natin siya na within the elastic limits. The strain produced in a body is directly proportional to the stress which causes it. So example, stress and strain, or stress, strain, constant yan sila. Stress over strain equals a constant. So yung constant natin is yung ating modulus of elasticity. So bumalik lang tayo dito sa formula nito. So elasticity, modulus, or modulus of elasticity. So here we have the types of strain. So yung strain is the change in dimension to original, change in dimensions to original dimensions is known as strain. So we have three types of strain: linear strain, bulk or volume strain, shearing or rigidity strain. So next slide, pag-usapan natin ang definition ng bawat strain na ito. So first, we have linear strain. Linear strain, where a wire or bar is subjected to two equal and opposite forces, namely pulls at its end, there is an increase in the length. If the force are tensile, the body is elongated. Kumbaga mahihila siya, hahaba yung ating body. If the forces are compressive, the length is shortened in the direction of the forces. So parang i-compress mo siya, iipitin mo yung body, so yung force na or stress na ma-feel nung ating object is compressive strength. So this is called the linear strain. The linear strain is defined as the ratio of change in length to its original length. If the change increase man or decrease in length is I, in a wire or bar, kumbaga yung ating object, wire or bar of original length L. As a linear strain is the ratio of lengths, it has no unit, so dimensionless siya. So wala tayong unit regarding sa ating linear strain. And then here we have its formula. So yung linear strain natin is equals to the change in length over its original length. Okay, so next slide. Here we have the bulk or volume strain. We defined a bulk or volume strain is when a force is applied uniformly and normally to the entire surface of the body, there is a change in volume of the body. Without any change in its shape, the strain is called bulk or volume strain. Volume strain is defined as the ratio of change in volume to its original volume. Kung kanina, yung linear strain natin is with regards sa length ng ating object, here sa volume strain is regarding naman sa kanyang volume of the body. Then again, it has also no unit. So yung ating A small letter B is yung change in volume produced in a body of original volume, o yung ating big letter or capital letter B. So yung formula para sa ating volume or bulk strain is change in volume over its original volume. So next is ang ating shearing or rigidity strain. So when a force is applied parallel to one face of a body, the opposite side being fixed, there is a change in shape but not in size of the body. This strain is called the shearing strain. Solids alone can have a shearing strain. It is measured by the angle of the shear, theta, and then yung ating theta is in radian. So here we have next is we have these three types of deformation or three moduli of elasticity. We consider three types of deformation and define an elastic modulus for each. So first we have Young's modulus, which measures the resistance of a solid to a change in its length. Next is shear modulus, which measure the resistance to motion of the planes within a solid parallel to each other. Last is yung ating bulk modulus, which measure the resistance of solid or liquids to change in their volume. So anong pinagkaiba or difference between these three types of deformations? So dito, sa ating Young modulus with respect to its length. Okay? Next is ang shear modulus is with respect sa kanyang motion. And then ang bulk modulus, again, with respect sa ating volume. Okay, next. Let's talk about the Young's modulus or elasticity in length. We consider a long bar of cross-sectional area A and initial length Li that is clumped at one end. Kung makikita ninyo dito sa ating figure 12.14. When an external force is applied perpendicular to the cross section, internal forces in the bar resist distortion or yung ating stretching. In such a situation, the bar is said to be stressed. We define the tensile stress as the ratio of the magnitude of the external force F to the cross-sectional area A. The tensile strain in this case, is defined as the ratio of the change of length delta L to the original length Li. We define Young's modulus by a combination of these two ratios. So, again, Young's modulus, or represented as capitalized letter E, it is defined as the ratio of linear stress to linear strain. Example, let a wire of initial length L and cross-sectional area A undergo an extension L, kumbaga yung change of length niya L, small letter L, when a stretching force F is applied in the direction of its length. The modulus of elasticity in this case is called, again, Young's modulus, and is given by linear stress over linear strain. So yung linear stress natin, ang formula niya is force over area. And then yung ating longitudinal strain is change of length over its original length. So i-ano lang natin siya. 'Di ba? Combination of these two ratio ang ating Young's modulus. So yung ating Young's modulus or letter E is equals to linear stress over linear strain, or F over A over L, small letter L over big letter L. So yung ating small letter L, balik natin, is yung change of length natin over its original length. Or, i-ano natin, simplify natin, yung Young's modulus natin is equals to force times yung original length over the area times yung ating change in length. So, ito. Ito yung formula ng ating Young's modulus. Next is yung ating bulk or volume modulus, represented as small letter k. It is defined as the ratio of bulk stress to bulk strain. When a body is subjected to a uniform compressive force, its volume decreases. Kasi gipiga mo giipit mo. So, kumbaga yung volume ng object magdi-decrease. And the strain produced is a bulk or volume strain. If small letter v is the change in volume and capitalized letter V is the original volume, then if F natin is yung total compressive force acting on a total area, then yung bulk stress natin is equals to force over area. Yung stress natin, parating ganyan ang kanyang formula, force over area, or is equals to pressure. Again, ang ating formula para sa bulk modulus is equals to bulk stress over bulk strain. So if P is the stress applied, yung ating force over area, then yung ating bulk strain is equals to change on volume over the original volume. So ang ating bulk modulus, ang formula niya is stress, yung ating P, or yung ating yung pressure, tama. Pressure times the original volume over the change in volume. So next is yung ating shearing or rigidity modulus, and it is represented in small letter n. It is the ratio of the shearing stress applied to the body. To the shearing stress produced is called the rigidity modulus, and it's denoted by the small letter n. If yung T natin is the tangential force per unit area, and then yung ating theta is the angle of shear measured in radian, then yung rigidity modulus natin is equals to tangential force, or yung ating T over theta, or force over area over yung ating angle of shear. Or itong kanyang figure na representation. So, kung itong ating original shape, itong box or rectangle shape, and then nung nag-apply tayo ng force, na-deform siya, and then meron tayong angle of shear angle. So, i-apply mo siya dito sa formula nito para makuha ang rigidity modulus. And then itong force na to given, and then yung area, kumbaga yung area ng ating rectangle, and then yung theta. So here we have the elastic modulus graph. So itong figure 12.5 is the stress versus strain curve for an elastic solid. So mamaya meron tayong video to represent this, mas maayos na representation ng itong graph na ito para mas maintindihan. So next is yung ating Poisson's ratio or sigma. When a tensile stress is applied to a wire, the wire undergoes not only an extension of length in the direction of the force, but also in a contraction in its thickness. The ratio of decrease in thickness to its original thickness in lateral direction is known as lateral contraction. The ratio of lateral contraction to linear elongation is called Poisson's ratio. So yung ating Poisson's ratio or sigma is equals to lateral contraction over its linear elongation. Don't worry, meron tayong video na ipi-play para mas maintindihan nyo at ma-visualize ng maayos itong mga terminologies na ito or mga factors na ito nag-act or magkakaroon ng effect sa ating object when we applied a deforming force. So before tayo mag-problem solving, i-play na muna natin yung video. So, sandali lang. So we have here an introduction to stress and strain. So let's play the video.
Stress and strain are fundamental concepts that are used to describe how a body responds to external loads. In this video, we'll explore these concepts using the simple example of a loaded bar. Here we have a solid metal bar that is loaded by two equal but opposite forces. We refer to this as uniaxial loading because all of the applied loads are acting along the same axis. The two forces are pulling the bar, causing it to stretch. Internal forces will develop within the bar to resist these applied forces. We can expose these internal forces by making an imaginary cut through the bar. I chose to remove the right side of the bar, but I could have removed the left side instead. For any imaginary cut like this one, the internal forces develop in such a way that equilibrium will be maintained. In this case, the effect of the internal forces acting on the cross-section created by our cut will be equal to the effect of the applied external force. I have represented the internal forces as 4 separate forces here, but I could have represented them as 1 or even 20 forces. In reality, the internal forces are distributed over the entire surface of the cross-section. For this reason, it doesn't make much sense to talk about specific internal forces. Instead, it is better to talk about stress. Stress is a quantity that describes the distribution of internal forces within a body. It makes it easier to discuss the internal state that develops within a body as it responds to externally applied loads. Stress is a measure of the internal force per unit area, and so has units of newtons per meter squared in SI units, and pounds per square inch in US units. Newtons per meter squared are also called pascals. In the case of our axially loaded bar, the internal forces are acting perpendicular to the direction of the cut we made. This type of stress is called normal stress. We can calculate the normal stress in our bar as the applied force F divided by the cross-sectional area A of the bar. It is denoted by the Greek letter sigma. One reason being able to calculate stresses is important is because it allows us to predict when an object will fail. Let's say our bar is made from mild steel, which has a strength of 250 megapascals. The bar will fail when the stress within it exceeds the strength of the material. If our bar has a diameter of 20 millimeters, for example, we can calculate that it will fail if the applied force is larger than 79 kilonewtons. Normal stress can be either tensile or compressive. In this case, the stress is tensile, because the forces are stretching the bar. If the forces were trying to shorten the bar, we would have a compressive stress. The sign convention that is normally used is that tensile stresses are positive values and compressive stresses are negative values. In the case of our bar, it is reasonable to assume that the stresses are distributed uniformly across the cross-section and along the length of the bar. But this is a very simple scenario. The stress distribution in a beam that is bending, for example, will be more complex. Stresses will be tensile on one side of the cross-section, but compressive on the other. Strain is a quantity that describes the deformations that occur within a body. If we fix our bar at one end and apply a force to the other end, the the force will cause the bar to deform. The normal strain within our bar associated with this deformation can be calculated as the change in length of the bar delta L divided by the original length L. Strain is a non-dimensional quantity and is often expressed as a percentage. Normal strains can be tensile or compressive. I mentioned earlier that the concepts of stress and strain are closely linked. The relationship between the two can be described using a stress-strain diagram. Stress-strain diagrams are different for different materials. We can obtain the diagram for a specific material by performing a tensile test. This involves applying a known force to a test piece and measuring the stress and strain in the test piece as the applied force is increased. Stress-strain diagrams for ductile materials like this one show that there is an initial region for low strain values where the relationship between stress and strain is linear. Deformations occurring in this region are fully reversed when the load is removed, and so are said to be elastic. This linear relationship between stress and strain is defined by Hooke's law. The ratio between stress and strain is called Young's modulus, which is an important material property. Hooke's law usually only applies for small strains. For larger strains, the relationship between stress and strain is no longer linear. Deformations are not reversed when the load is removed, and we have permanent plastic deformation. You can learn more about stress-strain curves in my videos about Young's modulus, and about material strength, ductility, and toughness. So far, we have only talked about normal stress, which is stress acting perpendicular to a surface. The other type of stress is shear stress. If our bar isn't loaded along its axis, but instead perpendicular to its axis, like this, the internal forces that develop within it are oriented parallel to the bar's cross-section. These internal forces are called shear forces. Shear loading is common in bolts, for example. Once again, it is helpful to use the concept of stress to talk about the internal shear forces within the bar. Shear stress is denoted by the Greek letter tau and can be calculated in a similar way to normal stress as the applied force F divided by the cross-sectional area A. This is actually an average shear stress, since the internal forces will not be distributed evenly across the cross-section. We can better understand shear stresses by looking at the stresses acting on a small element within our bar. We have a shear stress on one face of the element, but the element needs to be in equilibrium, so we must also have shear stress on the opposite face, in the opposite direction. And to maintain rotational equilibrium, we must also have two additional shear stresses, as shown here. These four stresses all have a magnitude equal to tau, and define the shear stresses acting at a single location. Shear stresses cause a rectangular object to deform, like this. We have deformation, so of course we also have strain. Shear strain is defined as the change in angle shown here, and is denoted by the Greek letter gamma. Hooke's law also applies for shear stresses and shear strains, but the ratio between them is the shear modulus G instead of Young's modulus. Although I have discussed normal and shear stresses separately so far, the stress state at a single point within a body will actually have components in both the normal and the shear directions. The magnitudes of the normal and shear components will depend on the angle of the plane we are using to observe the stresses. In our bar with uniaxial loading, the plane we used to make the imaginary cut was perpendicular to the axis of the bar, and so we had normal stresses but no shear stresses. If we instead use an inclined plane to cut the bar, we will have both normal and shear stress components. The stress element is commonly used to represent the stresses acting at a single point within a body. This is the stress element showing the normal and shear stresses acting at a single point for a two-dimensional case. For a three-dimensional case, the stress element looks like this. That's it for this introduction to stress and strain. Having a solid understanding of these concepts will be important for grasping more advanced topics like torsion and beam bending that I will cover in separate videos.
Okay, pause na. Okay, next video is para sa ating introduction to for the understanding of Young's modulus. Okay, let's play the
Welcome
video.
back to the Efficient Engineer channel, everyone. In this video, we're going to talk about Young's modulus, one of the three main elastic constants, along with shear modulus and bulk modulus, which are used to describe how a material deforms under loading. Let's introduce Young's modulus using the tensile test. The tensile test is a very common mechanical test, which takes a test piece and stretches it along its length. It is a uniaxial test, meaning that it applies a load in one direction only, as shown here. During the test machine measures the applied load and the change in length of the test piece. The main output from the tensile test is the stress-strain curve, which describes how much the material we're testing will deform for different levels of applied stress. Watch how the stress-strain curve evolves as we perform a tensile test on our test piece, which in this case is made of steel. The test ends when the material fractures. We can observe that the stress-strain curve is split into two regions, the elastic region, where the curve is linear, and the plastic region. If the applied stress is low and we remain in the elastic region, the original dimensions of the component will be completely recovered when the applied load is removed. For larger stresses that take us into the plastic region, permanent plastic deformation will remain after the applied load is removed. In the elastic region, the stress-strain curve is a straight line for most materials. This means the strain is proportional to the applied stress. Hooke's law gives us the relationship between stress and strain in this linear elastic region. The ratio between stress and strain is Young's modulus, also called the modulus of elasticity, which we denote with the letter E. It has the same units as stress, so PSI in US customary units and pascals in SI units. We can also measure Young's modulus as the gradient of the slope in the elastic region. Young's modulus is essentially a measure of how stiff a material is. The higher the Young's modulus, the stiffer a material, and so the smaller the elastic deformations will be for a given applied load. If we perform tensile tests for a few different materials, we will notice that the slope of the stress-strain curve is different for each of them. Different materials can have vastly different values for Young's modulus. For anisotropic materials like wood or composites such as carbon fiber, the value of Young's modulus will depend on the direction in which the load is applied. This graph shows the range of typical Young's modulus values for polymers, metals, and ceramics. In general, ceramics have higher values of Young's modulus, metals have slightly lower values, and polymers have much lower values. Why is Young's modulus different for different materials? Understanding what is happening at the atomic level can give us a better understanding of Young's modulus. On an atomic level, a material's Young's modulus is closely related to the strength of the bonds between its atoms. We can imagine these interatomic bonds as tiny springs connecting adjacent atoms. Elastic strain is the result of an increase in spacing between the atoms of the material and is resisted by the strength of the interatomic bonds, or the stiffness of the little springs in our model. This is very different to the mechanism behind plastic deformation, which involves rearrangement of the position of the atoms. This is why elastic deformations are reversed when the load is removed, but plastic deformations are not. I mentioned earlier that Young's modulus is smaller for polymers than it is for ceramics and metals. This is because it is the weaker intermolecular bonds in polymers that determine the material's stiffness, rather than the stronger atomic bonds. Looking at things on the atomic level can also help explain why differences in Young's modulus for alloyed metals tend to be small. Let's take the example of carbon steel. Mild steel and high carbon steel have quite different mechanical properties. Their yield strengths, for example, are very different, and yet they have very similar Young's modulus values, which at first glance might seem surprising. We can explain it using our interatomic bonds model. Mild steel has a carbon content of up to 0.25%, and high carbon steels can have a carbon content of up to 0.95%. Adding such a small number of additional carbon atoms to the existing iron atoms isn't enough to significantly affect the overall resistance to increasing the spacing between atoms. And so the Young's modulus is very similar for mild steel and for high carbon steel, despite some of their other mechanical properties being very different. Why is Young's modulus important? Young's modulus is a crucially important material property when it comes to engineering. In engineering design, a common objective for many different applications is to keep elastic deformations as small as possible, which means that Young's modulus is a key parameter that needs to be considered in the material selection process. Take the example of a bridge. If we construct a bridge from a material with a low Young's modulus, it will deflect a large amount when something crosses it, which is probably not the desired response. Selecting a high stiffness material would ensure that elastic deformations remain small for large loads. That concludes this brief introduction to Young's modulus.
So dito muna
If you have
magtatapos
any interesting facts
yung
about Young's
video for
modulus,
this,
let me know in the comments.
yung video na ito.
And stay tuned for more videos.
Oh. Okay, next video is the understanding of Poisson's ratio. Okay, let's play the video.
Hello everyone, and welcome to another video on the Efficient Engineer channel. In this video, we're going to take a look at a really interesting material property, Poisson's ratio. Poisson's ratio is such an important material property because it gives us key information about how different materials deform under loading. Let's get right into it. We can start with a quick example, the rubber band. If you take a rubber band and stretch it along its length will obviously increase, but it is also quite intuitive that at the same time, the band will get thinner. Poisson's ratio can tell us how much thinner the band is going to get. What about for a generic lump of material? Take this little orange cuboid. If we apply a compressive force to it, it will expand in the directions which are perpendicular to the direction in which we are applying the load. We call the direction along which the load is applied the longitudinal direction, and we call the perpendicular directions the lateral directions. If we reverse the direction of the force to apply a tensile load, the cuboid will obviously extend in the longitudinal direction, and it will contract in the lateral directions. The key concept here is that when you apply a load to a material in one direction, the material will also deform in the lateral directions. Poisson's ratio is the parameter that tells us how much the material will deform in the lateral directions.
With school, YouTube, and everything else I do online, it's hard to stay focused. That's why I like to use...
To find Poisson's ratio more precisely, let's take a closer look at the case where a tensile force is applied. First, let's give names to the various parameters involved. Lx, Ly, and Lz are the original dimensions of our cuboid along the x, y, and z axes. Delta Lx, delta Ly, and delta Lz are the changes in these dimensions after the load has been applied. They are shown as being divided by 2 because the change in dimension occurs on both sides of the object. Next, we can write out the strains in all 3 directions. As a quick reminder, strain is a measure of deformation and is defined as the change in length divided by the original length. It is denoted using the Greek letter epsilon and is usually expressed as a percentage. When we apply our longitudinal load, it turns out that the resulting strains in the lateral directions are equal. And here's the interesting part. They are proportional to the strain in the longitudinal direction. The ratio between the longitudinal strain and the lateral strain is actually a material constant. You might have guessed it by now, but we denote this material constant with the Greek letter nu, and we call it Poisson's ratio. By the way, Poisson's ratio is named after this guy, Simeon Denis Poisson, the famous French mathematician who formally defined the ratio in a note published in 1827. You might be wondering why a minus sign slipped into the equation. Remember that by convention, tensile strains are positive and compressive strains are negative. The minus sign is just there so that for the typical case where the lateral strains are opposite in sign to the longitudinal strains, we get a positive Poisson's ratio. Now is probably a good time to mention that this equation and the concepts described in this video only apply for isotropic materials, which are materials which have the same properties in all directions. We are also assuming that the materials are deforming within the elastic region. Things get a bit more complicated when plastic deformation is involved. Anyway, to summarize, Poisson's ratio is a dimensionless material property, which tells us how much a given material will contract in the lateral directions when we pull on it in a longitudinal direction. Now that we know what Poisson's ratio is, we can look at some typical values for different materials. Without getting too deep into the math behind it, it's useful to know that the theoretical range of possible values for Poisson's ratio goes from -1 to 0.5. In practice, most real materials have a Poisson's ratio of somewhere between 0 and 0.5. Most metals have a Poisson's ratio of around 0.3. Here are some typical values for a few selected materials. Now let's look at how different values of Poisson's ratio affect how a material deforms under loading. We'll keep things simple and consider a two-dimensional case. Most materials have Poisson's ratios between 0 and 0.5. When a tensile force is applied, these materials contract in lateral directions, as we have already seen with our orange cuboid. Materials with a Poisson's ratio of 0 are interesting. When a longitudinal tensile force is applied, there is no deformation in the lateral directions. One material that behaves in this way is cork, which has Poisson's ratio close to 0. This property makes it a very useful material for certain applications. A great example is the cork in a bottle of wine. Because it doesn't expand laterally when compressed, as you can see here, it can easily be inserted into the neck of a bottle. A material with a larger Poisson's ratio would be much more difficult to insert, as it would expand in the lateral directions when compressed. Finally, we have materials with negative Poisson's ratios. These are known as auxetic materials. They expand laterally when pulled and contract laterally when compressed, which seems counterintuitive. These are mostly engineered materials, like special foams, rather than materials occurring naturally in nature. This animation should give you an idea of how it is possible to get negative Poisson's ratios. You can see that as the material is compressed, both its longitudinal and lateral dimensions are reduced. For a typical material with a Poisson's ratio larger than 0, you would expect the lateral dimensions to increase when the material is compressed. Because it tells us how a material deforms, Poisson's ratio is a very important parameter in continuum mechanics for determining how a body responds to applied stresses. Let's look at a simple case of uniaxial stress, the tensile test. It is easy enough to determine the strains acting on a small piece of the specimen under test. The applied stress is a normal stress in the x direction, sigma x. The strain in the longitudinal x direction is simply given by Hooke's law, as sigma x divided by the Young's modulus E. Even though there are no stresses acting in the lateral y and z directions, there will be strains in these directions, as the material is contracting laterally. The strains in the lateral directions are obtained by multiplying the longitudinal strain by Poisson's ratio. This is just using the definition of Poisson's ratio, which we covered earlier. But what if we look at a more complex case, where we have triaxial stress with different stresses in all three directions. In this case, we can't just use Hooke's law to determine the strain in the x direction, because it will also be affected by the strains in the y and z directions. The simple version of Hooke's law for uniaxial stress no longer applies, because the strains in one direction will depend on the stresses applied in all three directions. We can use Hooke's law in combination with the equation for Poisson's ratio and the principle of superposition to obtain the equation for strain in the x direction. We can rearrange this equation into a more practical form, like so, and then apply the same process to obtain equations for strains in the y and z directions. These equations form what is known as the generalized Hooke's law and can be used to determine deformations for a case of triaxial stress. There is one last case I would like to mention, which is materials with a Poisson's ratio of 0.5, the maximum value in the theoretical range we discussed earlier in the video. Let's return to our cuboid to introduce the concept of volumetric strain. Volumetric strain is a measure of the change in volume of an object under load. I'm sure it will come as no surprise that it is closely linked to Poisson's ratio. We can calculate the volumetric strain by summing the strains in all three directions. Let's use the equations from the generalized Hooke's law we just covered to expand the equation for volumetric strain. We can then rearrange the terms to end up with the following equation. You might notice that something interesting happens to the volumetric strain when Poisson's ratio is equal to 0.5. We end up with a volumetric strain equal to 0. This means that for materials with a Poisson's ratio of 0.5, the volume of the material remains constant as it deforms. These are known as incompressible materials. Rubber is an example of an incompressible material. And that's it. We've reached the end of our review of Poisson's ratio.
Here,
if you enjoyed watching,
end ng
please remember to
ating
like and subscribe
video.
for more engineering videos.
So here, magta-tackle na tayo ng ating problem. So we have here problem number 1. Suppose that the tension in the cable is 940 Newton. So itong cable natin, may tension siya na 940 Newton. As the actor, itong nasa figure natin, as the actor reaches the lowest point, what diameter should the 10-meter long steel wire have if we do not want it to stretch more than 0.5 centimeter? Under this condition, so meron tayong mga given na tension force na 940 Newton, yung kanyang change of length na 0.5 centimeter, and then yung kanyang initial length na 10 meters, and then we have here yung kanyang Young's modulus value. So we have here, we have the cable, which is a steel. Ito nga, nakalimutan ko. So yun na yun. Steel cable. A steel wire, ayun. Ito. So, we have here 10-meter long steel wire. So, ang kanyang Young modulus value is ito. So, we have here steel. So, ito ang kanyang value. So, 20 times 10 to the power of 10 Newton per meter squared. So, ito yung ating i-consider na value ng Young modulus o yung ating Y. So, yung ating Young's modulus, ang formula again is tensile stress over tensile strain. So, from our previous discussion, yung ating formula for this is yung kanyang force, yung ating tensile force times yung original length over the delta L or yung change of length times yung area. So, meron na tayong mga value na to except doon sa area. So, kukunin natin ang ating area. So, F is 940. Ang kanyang original length is 10 meters. Okay? And then yung change of length natin, ano na natin in terms of meter ha. So, since 0.5 centimeter siya, magiging 0.05 a meter or 0.5 times 10 to the negative 2 meter. And then yung ating area ang ating hanapin. So again here, yung ating Young's modulus is 20 times 10 to the power of 10. And then unit na lang ito, Newton per meter squared. So, i-input sa calculator, shift solve, makukuha ninyo ang ating A na 9.4 times 10 to the power of negative 6 meter squared. So, we have the area na. Area ng ating steel wire. So, next. Okay, next. Kukunin na natin yung diameter. What is the diameter? Ito talaga yung question ng ating problem. So, from our area, kukunin natin, dito na natin makukuha yung ating diameter. So, ang formula para sa area is pi r squared or pi d squared over 4. So, ito yung gagamitin natin. Okay? So, yung area natin, i-substitute. So, meron tayong 9.4 times 10 to the negative 6 meter squared is equals to pi d squared over 4. So, pwede na din natin ito siya i-input sa calculator agad. Shift solve. Meron tayong diameter na 3.46 millimeter or mm. So, here ang ating answer for this problem. Okay. Okay, next problem natin is regarding sa ating shear modulus. So, a child slides across a floor in a pair of rubber-soled shoes. The friction force acting on each foot is 20 Newton. So, meron tayong force na 20 Newton. The footprint area naman of each shoe sole is 14 centimeters squared. And the thickness of the sole is 5 mm. Find the horizontal distance which the upper and lower surfaces of each sole are offset, or yung kanyang change in thickness. The shear modulus of the rubber is 3 mega Newton per meter squared. So yung given, ipang write up natin, pang write down natin. So may force tayo na 20 Newton. Yung area natin na 14 centimeter squared, or change natin, convert natin to meters. So meron tayong 14 times 10 to the power of negative 4 meters squared. And then, ang ating thickness, original thickness na 5 mm, or in terms of meters is 5 times 10 to the power of negative 3 meters. And then yung ating shear modulus na 3 mega Newton per meter squared, or 3 times 10 to the power of 6 Newton per meter squared. So ano yung ating change in thickness? So yung ating formula ng shear modulus is equals to shear stress over shear strain, or F of A over yung change of thickness over yung original thickness. So yung ating shear modulus is 3 at dito na tayo. So ipang ano na natin ha? Ipang substitute na dito sa formula na to. So meron tayong shear modulus na 3 times 10 to the power of 6 Newton meter squared. So per meter squared. So ito na. And then yung ating force na 20 Newton. Okay. Next, yung ating thickness na 5 mm, or 5 times 10 to the negative 3 meters. Okay. And then yung ating unknown, delta x. And then yung kanyang area na in terms of meter na 14 times 10 to the power of negative 4 meters squared. So isa na lang yung ating unknown. i-input sa calculator, shift solve, and then makukuha na ang ating delta x or change in thickness na 2.38 times 10 to the negative 5 meters, or kung naka-millimeter is 2.38 times 10 to the negative 2 mm. So, ito yung ating sagot sa ating problem. So here yung ating last problem for the elasticity of the objects, or itong topic natin na elasticity. So here we have a problem. A solid brass sphere is initially surrounded by air, and the air pressure exerted on it is 1.0 times 10 to the power of 5 Newton per meter squared, or yung ating normal atmospheric pressure. The sphere is lowered into the ocean to a depth where the pressure is 2.0 times 10 to the power of 7 Newton per meter squared. The volume of the sphere in the air is 0.50 meter cube. And then, by how much does this volume change once yung ating sphere is submerged? So again, i-write down natin yung ating mga given. So we have a P sub I, or initial pressure. So yung initial pressure natin is 1.0 times 10 to the power of 5 Newton per meter squared. And then yung ating final pressure na 2.0 times 10 to the power of 7 Newton per meter squared. And then meron tayong initial volume which is given na 0.50 meter cube. And then yung ating change in volume. What is our change in volume? Siya yung ating unknown. And then from the table, given table, yung ating bulk modulus para sa brass is 6.1 times 10 to the power of 10 Newton per meter squared. So here, ito yung data na kakailanganin natin. So, bulk modulus. So, solution natin for the bulk modulus, or yung formula natin para sa bulk modulus. Again, bulk modulus is equals to the volume stress over yung ating volume strain, or negative force over area over yung change in volume over the original volume. So since meron tayong initial and final pressure, so yung ating formula is madiderive into this formula. So masasum up with this formula. Ito yung ating i-consider na formula. So yung ating bulk modulus again is negative delta P, or yung change in pressure over the delta volume, or yung ating change in volume over the original volume, or yung ating initial volume. So here, yung ating delta P, or yung change in pressure is equals to the final pressure minus initial pressure. Okay, so ilipat lang natin yung ating formula. So yung ating original volume or initial volume is nasa taas na, over delta V, or yung ating change in volume. So with here, meron naman tayong value lahat na to except dito, diba? So isa yung ating unknown. So next slide natin. I-input na natin or substitute natin yung mga values ng ating problem, or yung given na ating problem. So we have the bulk modulus na 6.1 times 10 to the power of 10 Newton per meter squared. Okay, yung bulk modulus value natin is equals to negative yung ating final pressure na 2.0 times 10 to the power of 7 Newton per meter squared. Okay, yung final input na. Minus yung initial pressure, which is 1.0 times 10 to the power of 5 Newton per meter squared. Okay, na-input na. Times yung ating initial volume or original volume na 0.50 meter cube over yung ating unknown na delta V, or yung ating change in volume. So again, isa na lang yung ating unknown variable or unknown, unknown variable. So, i-input sa calculator, shift solve, may value tayo ng ating delta V na negative 1.63 times 10 to the negative 4, times 10 to the power of negative 4 meter cube. So, ito yung ating sagot sa ating problem. So, with this problem, dito nagtatapos yung ating discussion regarding sa elasticity. Okay, class, thank you. For the next video, wait for our next video, which is, ang topic is oscillation. Okay, thank you, class. See you in your midterm exam.